Welcome to my talk about new transports in Samba. I will be talking about the existing transports, NetBIOS, TCP, and then the new things, SMB-Direct and QUIC, and then how we support QUIC, how we support SMB-Direct, how we use IOU-ring on Linux to improve performance, and then I have a few slides with examples of where we stand currently. So I had a few presentations in the last years which are about similar topics. So if you're interested in more details, just take the slides later and have a look at the other presentations. So for SMB versions 1, 2, and 3, they all use basically the same protocol mechanism. So there is a message-based transport that transfers one or more SMB PDUs on top of that. And the oldest transport is the NetBIOS transport over TCP that uses port 139. And basically the header is always 4 bytes, but here it's just 17 bits for the length, and typically all other bits are 0. So for implementing this, it's very easy. So we just have the case where the header is just 16 bits length. Then we have direct TCP that's currently mostly used on port 445. It's 24 bits in length and increases the amount of data for a single SMB packet. And for us, both operate on BSD stream sockets for TCP, and because it's both 4 byte with just different width of for the length, it's basically identical to implement that. Then there are new transports, or it's 2026, and it was announced or started in 2011, so it's not really new, but new for Samba. It's SMB-Direct. It's a tiny layer on top of RDMA InfiniBand verbs. It supports InfiniBand, Rookie, V1, and V2. V2 is Rookie, basically InfiniBand over UDP, and there's iWarp that's based on TCP. So it basically has a very similar transport for the normal SMB packets. It's just allows payloads up to 1 megabyte. So it's a little bit less than what we have in for TCP, where we have 16 megabyte. But the thing is that the large SMB2 read and write operations, which transfer large amounts of data, are offloaded to RDMA read and write operations, which are use the same underlying transport, RDMA transport connection, but are out of bound for the stream-based transport. This was introduced in Windows 2012 together with the multi-channel feature, where clients start with the TCP transport and ask the server for interface addresses for multi-channel, and there is a bit that says this interface can do RDMA, and the client then checks its local capabilities, and if both support RDMA, they use SMB-Direct instead of TCP. And one important thing is that they always use IP addresses, even if they use raw InfiniBand. At the network layer, they use IP over InfiniBand. So the server never returns InfiniBand addresses, or only IP addresses. As I said before, the read-write operations can offload the data transfer to RDMA read and write operations, which makes it much more efficient for client and for server. Basically, more on the client, but basically the server reads and writes directly into the client's memory. And one important confusion or important thing is that the SMB2 reads use RDMA write, and the SMB2 write use RDMA read. So it's sometimes a bit confusing, but that's how it is. Then more recently, the QUIC transport was added. QUIC is a TLS 1.3 based protocol on top of UDP. It's basically designed for HTTP 3 with security, performance, and robustness in mind. It uses UDP port 443, so it that should go through firewalls and routers and so on. And the thing is that it supports an application protocol negotiation, and there the client says, I want to talk to the HTTP server with H3, or to the SMB server specifying SMB. But other than that, there's no indication what is inside of the encrypted traffic. On Windows, this was introduced with Windows 2022. It basically tries TCP first and then falls back to QUIC. And the thing is that while the QUIC protocol in general supports multiple logical streams over single connection, SMB only uses a single one, so it's very easy for SMB to make use of that. And also there we have the 4-byte header, 24 bits of length, 8-bit 0, and so it's the same as TCP. So all logic above that is exactly the same for the SMB handling. But the important thing is that the client needs to know the server, and it would be good, or in some situations important, to verify the server certificate, but as there's SMB3 encryption on top of it, the admin can also decide, I just want to use that, but from the security point of view, for me it's just like TCP. I just use it to get through the firewalls or so, and so it's not that important if SMB3 encryption is used. So yeah, basically for testing, or in some situations it's possible to just say I disabled certificate validation for that case, because I'm fully fine with the SMB3 encryption, which is based on the username or the user credentials, while the transport encryption is just based on basically the server and client machine credentials. Windows 2025 introduced some new features that make it possible to disable this double encryption where client and server negotiate. Now we both agree that quick encryption is good enough, and in this case obviously client, and it's also possible that the server can require a client certificate, but basically the client has to verify the server certificate to make this secure. And in that case, on the SMB3 layer, the encryption is just ignored and doesn't happen. So, having QUIC support in Linux is something that's on its way. So there's a QUIC KO module that provides basically a BSD stream socket for QUIC support, and it will just use the normal socket API when just with IP proto QUIC instead of IP proto TCP. And then user space needs to call the QUIC handshake function, which does the cryptographic setup before the connection can start. And from there, it's basically just like TCP and very easy to do. Yeah, and for Samba, it's also very easy to do. We just need to switch from IP proto TCP to QUIC. And as we already use GNU-TLS internally, that makes it very easy to hook into this QUIC handshake, because it also uses GNU-TLS based structures. And from there, it was relatively easy to implement. The most challenging part was to have the infrastructure to pass down the SMB client SMB transports and server SMB transports down all the stack layers from the higher level down to the low level socket interaction, and also that the SMB status JSON output announces the correct transport. The Linux QUIC KO will hopefully mainline soon. The 11th revision of patches was posted a few weeks ago, and with a bit of luck, the next Linux 7.2 release might have it. So we're currently in the merge window of 7.1. Maybe the next one will get it. Then, as QUIC is based on UDP, it's also possible to do everything in user space. And for that, on the client side, we make use of the libng TCP2, which also makes use of GNU-TLS, and it's very easy to hook this into our T-Vent non-blocking infrastructure. Yeah, it was relatively easy to make this work, and that means we could also use QUIC on a client on non-Linux systems. For the server, it's a bit different because we rely on sockets and FD passing for multi-channel, and that would be very complex with UDP sockets, which are shared between connections, so we don't have that. So now to SMB-Direct support in Linux and Samba. The Linux kernel already had some support for SMB-Direct for the sysko, the client module that has an RDMA mount option. The server KSMBD also listens on available RDMA interfaces, but in the past both had their own implementation, partly copied from each other, but both with a few bugs here and not there, and missing features in the one thing and not in the others, and so on. So in the current 7.1 merge window of Linux, that include a new SMB-Direct.ko module, which I implemented. It's basically a long journey of about 420 small patches. First, bringing everything together with shared structures in the C code, then making sure the logic in client and server is implemented the same way, and then moving that logic into a new module which both can just use. And from there I have patches to implement an IP Proto SMB-Direct for use in SIPS-KO and KSMBD, so that they can just use the generic socket layer and don't have special cases for TCP and SMB-Direct, and later also for QUIC. That's relatively easy, and on top of that I have in SMB Proto, IP Proto SMB-Direct implementation that is also usable for user space. That basically works, and I don't see much problems with that, but there's still some work to do to clean up and make things more like a generic socket in the kernel. So for only in-kernel users we can have the logic as we currently have it, because it doesn't change anything. But some parts for user space access, it's important to be more like a TCP socket and behave like that. On top of that, I have the Samba part basically finished, so there's a merge request and it's still marked as draft, but basically only because the kernel part is not written in stone yet. But it shows very good results already. Then, as we basically the last 15 years try to do always, is to have Samba regression tests and make sure every single commit keeps working and so on. So for that we have socket wrapper for Samba testing, which emulates TCP and UDP sockets over Unix domain sockets and use LD preload and things like that. And the recent versions also have basic support for QUIC sockets, which just use the SIG packet way of implementing things in the Unix domain sockets, which basically provide very similar behavior than what the QUIC kernel module implements on top of UDP in the kernel. And then we recently got basically the emulation for SMB-Direct, but it basically just uses TCP sockets or TCP emulation for now. Yeah, we have the QUIC-KO wrapper now, which emulates the QUIC-KO module. It's basically implemented on top of socket wrapper, and it uses the libng TCP2 for the crypto things. Then we have the SMB-Direct KO wrapper, and yeah, that's basically underneath looks like a TCP socket emulated by socket wrapper, with the addition that we have a few special ioctls in order to do the RDMA offload and use the process VM, read V and write V syscalls in order to directly write into the memory of the other process. And yeah, these are good enough for basic regression testing in Samba and explore the code path we are using there. So from there, over the years, we always had the wish to make more use of the IOU ring infrastructure in the Linux kernel, and because it's very evolving and adds more features in each kernel release, and it's good to have a abstraction in Samba that makes it possible to implement everything without using if-defs and special and complex code that works when we have this installed in the system. And so basically we have an abstraction now that only or checks what the kernel currently supports, and then we have the Samba IOU feature structure where we have Boolean values for every feature we have there. And the other important thing is that we attach that to our T-event contexts. So we pass T-event context basically through almost all layers in Samba, and now when we have the global event context in the SMBD, we attach the IOU ring context to that, and we have a function that tries to get the IOU ring context from the event context, and if it's there, it's possible to make use of it, and then makes it very easy to do that in isolated places without the need to pass down the structure explicitly. Basically, yeah, we had the VFS IOU ring module before, and I basically took the core logic of that and abstracted it out, and now we have the this directly as an T-event backend, and that awards if-defs and so on. So the generic API for that is that we have a completion prepare that gets the completion function, a submission prepare that gets a submission function, which basically prepares the IOU ring submission queue entry, and then we have, because it's possible to link multiple operations together, we first have the submission SQE function that gets the SQE to be filled, and then we have queue submissions where we basically add the submission to a linked list at the end, and then we have the submit SQEs which basically do the syscall to transfer this to the kernel. And for with this API I converted the VFS module, and then in the next steps I converted the SMBD server logic. And for testing I also did something in the client, but that needs more additional work in future. So this gives a very great performance boost, but but also tells us that the performance was not good in current SMBD scenarios where the send message and the receive message syscalls are real performance killers for that. They basically block the main SMBD process for the client and just use the CPU SMAT and in order to copy data from the user space SMBD memory to the socket basically. And even high-speed networks, we only get a few gigabytes per second with this, depending on the hardware. I saw sometimes just 3 gigabytes per second or 7 gigabytes per second on newer machines, but so basically this is bound to the CPU and the ability to do the mem copy, and it's not bound to the network interface. So I refactored the SMB2 server code in order to optionally use the send message and receive message hooks from IOUring. And there we use the async flag in order to do the mem copy in helper threads. That means that the main SMBD logic is more or less non-blocking now, and it improves the multi-channel experience by something between 30 or 100%, depending on the setup. So in the first experiments I did a few years ago, we got from 3 gigabytes per second to 7, and in newer situations we get from 7 to 10 or so. So it also depends on the hardware. Then there is a send message zero copy, which means we can avoid copying data in the path from SMBD to the socket. And it works like this, that we submit the send message operation, and that completes in its normal fashion when the TCP layer has processed it, but the user space memory is still used by the TCP stack for retransmissions and so on. So we only get a second IOUring completion when the kernel no longer needs the memory. And this needs real network hardware to work on loopbacks. That doesn't work, but it improves also on top of the other improvement by something between 30 and 60%, depending on the setup. And the most important thing is actually reduces the server CPU usage by 100 or more %. For now it's TCP only, but in future SMB-Direct will also follow. So the next also important performance boost is using the splice operation. That basically avoids memory copy completely. In the way from the socket via a pipe to the file system, we only avoid one copy. Basically, we use the kernel pages we got in the socket, moving this to the pipe with basically zero copy. But because of restrictions in the kernel on the file system layer, from the pipe to the file system, we still see a copy of data. As well, currently TCP only, but it should work without problems. And for RDMA, it's not that critical because the huge data transfers are offloaded to RDMA read anyway, so it's not so important. For the other direction with splice from the file system via the pipe to the socket, we can have full zero copy, basically from the file, from the page cache to the pipe. Then we use send message or send message zero copy for the SMB header, and then we use splice again for the data to the socket. And with TCP, this is basically also zero copy. For RDMA, I have a special IO command which does a remote write using splicing from a pipe, and that is used for the RDMA write offload. The only problematic thing is that there are structural problems with splice from a file. So when we have pages in the page cache, we can reference them and send it to the socket. But if the same client or a different client actually changes the file, these changes are reflected in the page cache, and that means the pages in the network layer are modified, and maybe the checksums and so on and signatures would not match anymore. That's because we may not use this by default and only on read-only shares or so. But looking at the code, there might be tricks to avoid that, and stealing pages from the page cache, or doing async mem copy using the DMA engine and so on. But I need to experiment with that a bit more. Then we bought a test setup for performance and RDMA testing. We have two servers, AMD Ryzen 9 and with 16 cores, 96 GB of RAM, PCI 5, fast SSDs and so on. And basically there I use Ubuntu 26.4 with the custom kernel and a custom Samba version. Then we have Mellanox Connect X7 with Roku V2 and two 200 gig ports, and they're connected just with direct cables. And for functional testing, we also have Intel RDMA cards and Chelsea cards, which will also be added to the box when we don't do performance testing, because otherwise the Mellanox card would only get half of the PCI bandwidth and so on. So for performance, I just have the Mellanox cards in there. And with that, we have an SMB2 bench read benchmark. When I use this with I/O size of 2 megabyte and use TCP and splice in the Samba case, I'm basically able to have a single SMB torture command getting about 20 gigabytes per second, and it uses about 700% CPU on SMB torture, and I only got that because at the lower level I'm also using the IO based receive message in the receive part. Otherwise we would have the same problem as SMBD, where we block, and we were bound by the client CPU. But the interesting thing is on the server side, with that we actually only have about 70% server CPU of one CPU. So we have 8 connections and so on, but as we see here, we use the client GUID option of SMB Torture, which means based on the client GUID, all connections would end up in the same SMBD on the server side, and basically serving 20 gigabytes per second over TCP, and from there it's a limitation on the TCP stack, at least as far as I can see. So the network side would allow much more, which we will see with RDMA in the next slides, but I think that's, even without RDMA, a very good result. And with PerfTop we see basically we don't do any mem copy or copy at all, only page management and so on. And for RDMA offload, I first have a picture here where we have 2 SMB torture commands running on the same client using the same client GUID, so they simulate a single client and uses both RDMA interfaces with 2 times 200 gigabit. And with that, we see basically 46 gigabytes per second on reads from the Windows host. And this shows from Samba we are basically getting the same performance using the splice from the file system and then from the pipe directly to the RDMA write offload. And for that, on the client side, we see just 2 SMB torture commands, both using about 33% client CPU, and compared to the 700% CPU for the TCP case, this is basically nothing, and more than twice in bandwidth. On the server side, we just have about 250% CPU, and that's basically split up in 82% on the main SMBD, and then a lot of IOU ring helper threads, which are blocking here. But I all these in status D have plans how I can avoid that, so that we only have a few of them instead of a lot of them with just 5%. But here we see page cache buffer releasing is the only thing that pops up in PerfTop. Then we have the same for Samba with 8 megabyte IO size. Then we get the same performance out of it, but use less connections. And the SMB torture commands use way less CPU, and also on the server side we just use 110% CPU, so a little more than 1 CPU. And the thing is that the main SMBD basically just uses 22%, and the rest is IOU helper threading. And also here with PerfTop, We just have page management stuff. Yeah, that means we are basically back in the game and are able to handle high-speed networks, and there's no longer need to use proprietary SMB stacks on Linux to get there. And basically it all depends on the disks and the file system performance now. And if everything goes well and as expected, we will have that in the next Samba release in September, together with direct releases and persistent handles. And I think that would be a good future for Samba, actually. And with that, I'm finished with my talk and open for questions.